Hi everyone, this is Guo Chushan. Today's topic is scale-equivalent distillation for semi-supervised object detection. Deep supervised learning is a subfield of machine learning, which requires a large amount of annotated data. The well-known image classification dataset, ImageNet, contains about 1.28 million labeled images. A large object detection dataset, COCO, is composed of only 0.1 million labeled images. However, human labeling is time-consuming and expensive, especially for the complex annotation. Semi-supervised learning solved the problem by utilizing a few of labeled data and a large amount of unlabeled data to train a model. Applying semi-supervised learning to object detection is challenging because of the large variance of object sizes, massive false negative samples and class imbalance problem. There are multiple instances in a single image for object detection. Besides, the size of instance varies in a wider range for COCO dataset than ImageNet dataset. An ideal detector is supposed to be scale invariant. The predictions of an image in different sizes should be consistent. However, we observe a discrepancy in objectness score. As shown in the left figure, the kite is predicted with a lower score in the small image than that in the large image. As for the snowboard, the detector doesn't recognize it in a small size. But the model detects the snowboard in the large size. We analyze the score distance between instances in two different sizes. The yellow curve indicates that the ratio of foreground sample to background sample increases as the score distance becomes large. It implies that the model detects an object instance while is blind to the instance in another size. Current semi-supervised object detection methods are based on self-training. Object detector based on self-training suffers from the false negative instance noise, because many foreground instances are scored lower than the threshold. The false negative instance noise will cause a recognition inconsistency. Besides, the precision at 0.9 is less than 0.2. This shows that the location of pseudolabel is not accurate enough. Modern CNN object detector is sliding window. The foreground instance area is usually less than the background. The right figure is a label assignment illustration of RetinaNet and FCOS detector. We can find that the background label is majority. Identifying foreground regions from the unlabeled data with the overwhelming background regions is challenging. To overcome the challenges mentioned above, we propose scale-equivalent distillation. We design a scale consistency regularization across the prediction in different sizes as a solution to the large object size variance. Besides, we adopt a self-distillation method to generate more accurate label from a teacher. The teacher shares the identical architecture and update the parameter from student model weight in an exponential moving average manner. We also propose a re-weighting strategy to focus on the inconsistency among foreground regions. This is the overview of SED. The supervised branch shares the student model with the unsupervised branch. For unsupervised branch, the images with strong augmentation are input to student model. The network outputs a pyramid of score maps. We shift the pyramid score maps and penalize the distance between score maps. This regularization encourages the detector predict consistently for different size image. The resized image attaches an additional memory and computation cost. The teacher is input with weakly augmented image to ensure the quality of soft pseudolabel. There is no hard threshold and the soft pseudolabel is generated in one stage, unlike the two-stage self-training methods. The re-weight strategy aims to reduce the discrepancy for the potential foreground instances. In the left figure, we observe that the foreground samples are more likely to have large score distance. That means the hard samples should contribute to the gradient more than easy samples. We calculate the accumulated gradient and find that the easy samples contribute significantly because sample number is too large. Therefore, we re-weight the gradient by the sample numbers in a gradient range. Specifically, we split the gradient range into n bins equally, and average the gradient for each bin. The reformed gradient linearizes the relationship between gradient contribution and score distance. Finally, I'd like to show you the superior result of SED. In this table, all the SSOD methods are based on faster RCNN detector with ResNet 50 backbone. SED surpasses the supervised counterpart by more than 10 map when only 5 and 10% labeled COCO data are used. In conclusion, SED is a consistency regularization-based semi-supervised object detection framework. The proposed scale consistency regularization, self-distillation and re-weight strategy jointly overcome the challenges of SSOD task. Furthermore, SED is a holistic approach, which compatible with other methods, such as mix-up and domain adaptation method.